We take for granted every day that what we perceive as real is actually reflective of some type of objective reality, that the atoms and molecules composing our bodies exist, that the photons interacting with us possess energy and momentum, and that the neutrinos passing through us are bona fide quantum particles. But perhaps the universe, from the tiniest subatomic particles to the largest collections of galaxies, doesn't exist as a physical entity, but merely as an illusion in some other truer reality. It might sound like a plot from a sci-fi tale, but there could be some scientific basis to it. The concept of our daily experience being false or illusory is a recurring theme in philosophy throughout history. One famous example is Plato's allegory of the cave, presented in his work The Republic around the 4th century BC. Plato likened humans to prisoners in a cave, mistaking shadows of people and objects projected on the cave wall for reality, without realizing they are just dim copies of the real beings outside the cave. Another example comes from the French philosopher Descartes in his Meditations on First Philosophy from 1641. Descartes imagined a malicious demon deceiving him, making him doubt the reality of everything around him. From this doubt, Descartes concluded the certainty of his existence as a thinking being, but he remained unsure about the truthfulness of his ideas about the world, except by relying on the belief that they come from a perfect and infinite being, who cannot deceive. The notion that the universe around us might be an elaborate illusion likely stems from the mediated nature of knowledge. We perceive things not as they are in themselves, but as they appear to us through our senses and cognitive abilities. The fundamental challenge here is the gap between perception and reality. Philosophers like Immanuel Kant have articulated this as the distinction between things in themselves and things as they appear. This distinction suggests that our understanding of the universe is inherently constrained by the tools with which we perceive it. Experience has shown us that our senses and reasoning can sometimes deceive us. Optical illusions, mirages, and dreams provide everyday examples of how easily our senses can be deceived. In more complex scenarios, such as the interpretations of quantum mechanics, our intuitive grasp of reality is further challenged, suggesting that what we perceive as solid and certain may not be an accurate reflection of the underlying nature of the universe. The most complex knowledge is built upon basic elements, and if these foundational elements are partly illusory, then everything built upon them could also be illusory, even if it seems coherent to us. In recent times, this ancient idea has taken the form of digital simulation. Over the past 60 years, the exponential growth of computing power has made it plausible, shifting from science fiction to a conceivable reality, to create simulated worlds that are increasingly realistic, populated by beings like us who are unaware that they exist within a simulation. The Matrix trilogy is a popular cinematic portrayal of this possibility. One of the enduring mysteries of science is why the laws of nature are precisely what they are. Why does the universe have only a specific number of fundamental particles, forces, and constants that govern everything? Currently, there is no mathematical or physical theory that dictates exactly how the universe must be, or that allows us to discern the full nature of reality. We're part of the universe too, so we can only see so much of it and only to a certain level of detail. Some of this is because our tools have limits, but some of those limits are just built into how things work. In the observable universe, we can't see anything farther than 46.5 billion light-years away in any direction from Earth, because there hasn't been enough time since the Big Bang for light to reach us from beyond that point. Also, our technology limits us from investigating distances smaller than about 10 to the power of -19 meters. But even if we had perfect technology, there's a fundamental limit to how small we could go, at about 10 to the power of -35 meters. Plus, when we try to measure certain things at the same time, we run into fundamental uncertainties because of the limits of what we can know in quantum mechanics. If computing power reached extremely high levels, we could potentially simulate every single particle in the universe throughout its history. A quantum computer, capable of maintaining each particle in an uncertain quantum state, might incorporate this fundamental uncertainty. If such a simulation led to planets with intelligent life, could they figure out they're in a simulation? Some scientists argue that since even continuous things like time and space appear to have quantifiable limits, our universe is both computable and finite, making simulation possible. However, this perspective might not hold true in physics. Quantum uncertainty is real, but it doesn't necessarily mean that space and time are quantized or that photon energy can't be infinitely small. While the observable universe might be finite, considering the unobservable universe could render it infinite. Additionally, we employ various methods to simplify the computational burden of our simulations. If the universe used similar methods, we'd observe blurred results in experiments at small scales, which isn't the case. While it's true that information theory principles often appear in cutting-edge theoretical physics, this could simply be due to both fields following consistent mathematical rules. In other words, the integration of information theory with physics often arises not necessarily because the universe is computational by nature, but because both fields utilize similar mathematical frameworks and concepts. This alignment doesn't inherently validate the computational nature of reality, but highlights the usefulness of computational and informational concepts in describing complex physical systems. Some arguments, like the idea that because it might one day be easy to simulate a mind, there will eventually be more simulated minds than organic ones, are simplistic and easily debunked. For instance, why would someone with the ability to simulate an entire universe be interested in simulating a human mind? Philosopher Nick Bostrom, a professor at the University of Oxford, introduced the simulation problem by envisioning the potential for almost limitless growth in computing power. In a 2003 article, he presented a trilemma, which consists of three mutually exclusive propositions, one of which must be true. The human species is likely to go extinct before reaching a post-human stage, defined as a technologically advanced civilization with computers far more powerful than today's supercomputers. Any post-human civilization is unlikely to run a significant number of simulations of their evolutionary history or variations thereof. We are probably living in a computer simulation. In simpler terms, Bostrom's trilemma suggests that if our descendants avoid extinction and reach a highly advanced technological level, they could create simulations of their ancestors, which would be indistinguishable from reality for the simulated beings inhabiting those universes. It's possible that future civilizations might choose not to use their advanced technology to simulate their ancestors, or they might do so only occasionally. However, if civilizations in the future heavily rely on such simulations, the number of simulated minds could eventually outnumber natural ones by a huge margin. In such a scenario, it becomes highly probable that each of us is not a real human being but rather a digital mind within a simulation created by descendants of humans like us. These digital minds would believe they live in the physical world, unaware that they actually inhabit a digital universe. Bostrom's propositions are based on the idea that the mind and self-awareness can arise outside of biological bodies created by evolution. According to this hypothesis, advanced technologies could create simulations of the universe so detailed and realistic that they could produce thinking beings like us. To these beings, the simulated reality would seem like the only actual reality, because it's in the interest of the simulation's creators that the simulated ancestors remain unaware of their simulated existence. If our world is a simulation, how could we detect it? One possibility is through software bugs. Even the most advanced digital programs have flaws, leading to unexpected events that the program can't handle. However, if we truly live in a simulated universe and the creators have done an excellent job, no simulated mind would remember encountering a bug. The creators could reprogram the memories of simulated ancestors, erasing any dangerous memories that raise doubts about their world. Alternatively, the creators might choose not to intervene, even if the simulated minds discover clues for scientific reasons. In this case, it's theoretically possible to discover that you're living in a simulated universe. This possibility doesn't rely on software errors, but rather on the limits of computing power. Even a highly advanced civilization must contend with the limitations of their computer's calculations. Therefore, they must find ways to conserve resources. For instance, if the goal of the simulation is to observe the evolution of ancestors of a post-human civilization on Earth, is it necessary to simulate all the stars and planetary systems in the observable universe's approximately 2 trillion galaxies? It might be more practical and cost-effective to only approximate the farthest objects, fooling even our most powerful telescopes and convincing simulated astronomers they're observing real, distant galaxies. Similarly, when considering the incredibly small scale, Is it essential to replicate the nuclei of every atom down to the femtometer scale? Wouldn't it be cheaper to allocate computational resources to simulate them only when someone within the simulated universe observes things at the femtometer scale? In this scenario, if the simulation's creators effectively manage their computing power, the simulated minds wouldn't notice anything unusual. When they observe far into space or delve into the submicroscopic world, they would find everything seemingly real because it aligns with their expectations. In essence, the only chance to uncover clues of our universe's simulated nature is if we happen to be the subjects of a somewhat primitive simulation, despite the vast resources available to a post-human civilization. In such a case, limited computational resources might lead us to discover, by scrutinizing details to the utmost limits, that our universe isn't physically real, but rather a simulation. The primary clue that our universe might be a simulation with limited computing resources would be the discontinuity of space-time. Instead of being continuous, space-time would appear to consist of discrete intervals, as if it had a granularity. This discontinuity would result from a grid of points at the base of the simulated universe, representing the minimum intervals along which movement is possible. At a small enough scale, it would be observed that one cannot move from position 1 to position 2 by passing through an arbitrary position like 1.5. Instead, one can only jump directly from 1 to 2. Similarly, objects cannot have sizes like 1.5. They can only be size 1 or 2. Below size 1, no further structure would be discernible. So far, no experimental evidence indicates that the universe we inhabit possesses such granularity. However, a 2015 study by Eric Perlman and colleagues aimed to investigate whether space-time structures could exhibit fluctuations predicted by quantum mechanics on very small scales. The study didn't directly address the hypothesis of a simulated universe, but was relevant to the concept of space-time granularity. Several theoretical models of quantum gravity suggest that at the Planck length, space-time may not be continuous, but instead composed of small bubbles, resulting from quantum fluctuations. Visualizing this submicroscopic reality is challenging, but a useful analogy might be flying over the ocean at a high altitude. The water's surface appears continuous, flat, and uniform from such a height. However, as you descend, you begin to see the crests and troughs of waves. Moving closer, you eventually observe the foam forming on the crest of the waves. Directly observing quantum foam is impossible due to its existence at scales billions of times smaller than that of an atomic nucleus. However, its effects could potentially be observed on much larger scales, such as those of the most distant galaxies. This was precisely the aim of the experimental verification attempted by Perlman and colleagues in their study. According to quantum gravity models tested by the authors, the fluctuations forming quantum foam would accumulate over time and distance, potentially blurring or even erasing images of celestial objects billions of light-years away. To test this, the authors analyzed images of distant quasars acquired in X-rays and gamma rays from space and terrestrial telescopes, searching for blur effects that could confirm or disprove the considered quantum gravity models. However, the images of the observed quasars in high energies turned out to be clear and well-defined, suggesting that space-time maintains a uniform and continuous structure, free of quantum bubbles, even on a submicroscopic scale. In essence, the study's results suggest that at least two models of the universe examined are incomplete or incorrect. The examination of light from distant quasars is compatible with a continuous space, devoid of irregularities, up to distances 1,000 times smaller than the size of a hydrogen atom's nucleus. This finding allows us to dismiss, at least up to that submicroscopic scale, the hypothesis of living in a primitive simulation with a grid of minimum distances capable of being revealed by the degradation of images of celestial objects like quasars and blazars. Another potential clue to discerning a simulated universe lies in the distribution of cosmic rays at the highest energies. A study published in 2014 by Silas Bean and other colleagues discusses this topic. The authors calculated that the distribution of the most energetic cosmic rays should exhibit symmetry breaking if we inhabit a simulated universe with limited computational resources. While experimental data on the most energetic cosmic rays show a similar limit, it may not necessarily be linked to the simulated universe theory. Indeed, it's an intriguing idea that sparks the imagination. We can certainly limit this hypothesis by studying space, time, matter, and energy with greater precision and energy levels. However, throughout history, our understanding of reality has advanced by asking deeper questions about the universe in innovative and fundamental ways. Resorting to the simulation hypothesis as an explanation for current perplexing questions can feel like abandoning scientific inquiry, akin to appeals to the anthropic principle. Nevertheless, assuming that the universe is finite and therefore the resources of potential simulators are finite, then a volume containing a simulation will be finite, and a lattice spacing must be non-zero, and therefore in principle, there always remains the possibility for the simulated to discover the simulators. Discovering evidence, such as from cosmic rays, that spacetime is discrete would greatly enhance our understanding of the universe. However, it wouldn't prove the simulation hypothesis. In fact, there's no definitive way to prove it. Any anomalies we uncover or fail to uncover could be inherent properties of the universe itself, or parameters intentionally set or adjusted by hypothetical simulators. Philosophically, the idea might be attractive to a civilization envisioning the creation of artificial intelligence. Indeed, we don't assess the scientific validity or likelihood of an idea based on its appeal. Physics captivates us precisely because of its counterintuitive nature and predictive power. Even if we were actually living in a simulation, it shouldn't deter our pursuit of understanding the laws of nature, the origins of those laws, or why fundamental constants have their specific values. Because we're in a simulation doesn't serve as an answer to these questions. Rather, it becomes an integral aspect of our reality. Saying we're in a simulation is akin to stopping at a mystical explanation. It doesn't advance our understanding, but rather stalls it at a metaphysical assertion. Scientific methodology requires that we move beyond such assertions to continue to test, predict, and understand the universe, whether it is simulated or not. The pursuit of understanding the origins of laws of nature and why fundamental constants have their specific values remains a crucial endeavor. This pursuit would be essential even in a simulated reality, as understanding these laws would enable us to navigate and potentially exploit the system in which we exist. While the simulation hypothesis offers a philosophical perspective, it does not halt the progress of science. Instead, it presents yet another layer of complexity in our endless pursuit of understanding the universe. The mysteries of nature remain as challenges for us to unravel, and it's still our responsibility to seek solutions to them. And that's it for the video. Do you think we live in a simulation or not? I'd love to hear your thoughts in the comments section. Thanks for watching, and subscribe for more videos.